Hello, I'm Leo Scott, and welcome to this companion video for Inside OpenFlow's article on custom Mininet topologies and introducing Atom. This is our main segment and will cover creating and testing custom Mininet topologies. Viewing the previous segment on Atom is not required, as you are more than welcome to use whatever editor or IDE you wish. However, we will be showing Atom as the IDE in this video, as we did in the screenshots in the full article. As before, this is an overview article and will not cover everything in detail, but it will show the process from start to finish to make it easier to review and check against your own work. For detailed instructions, see the full article linked in the description below. To get started, open Atom and minimize it so it can be controlled on the command line. Now let's create a new project directory for our custom Mininet topologies. Open a terminal and create the project directory at ofworkspace/mininet-topologies. Change to that directory. If using Atom, go ahead and add it as a project folder by running atom-a for the current directory. For this video, we'll be using the downloadable package that includes all the example code in the article. If you've downloaded this package, go ahead and extract it into the workspace directory. The source code should now appear in Atom as well. The first Mininet topology we will cover is really the simplest. It includes only the essentials to create a single switch, two hosts, and a single link between each host and the switch. The file displayed here also includes the bootstrap code, but that can be ignored for now. The code that really matters is the code here. It includes a build definition that instructs the topology to add two hosts, a switch, and links between the host and the switch. This topology can be run quite simply by starting Mininet with the -- custom option pointing to mininet.py file and the -- topo option specifying minimal as a topology to use. The rest of the options are the same as the previous articles: automatic numbering, open vSwitch switch, and use a separate OpenFlow controller. From the output, you can see that two hosts were added, a single switch was added, two links were added, and two hosts configured. The controller, which is remote, so is a null operation, and then finally start the switch. Now, start the controller with the OpenFlow 1.3 version of the Simple Switch Ryu app. Optionally, also load the OFCTL REST API if you wish to poke around. See the Interactive Ryu with Postman article for more information on using the REST API. Performing a ping all command results in no packet loss. There is an alternative way to run the minimal topology as listed in the article by using the bootstrapping code added. This won't be used in the later topologies in the article, but it can demonstrate the ability to create a script that will configure all of Mininet rather than specifying command line parameters. This is used later to run the unit test for all the topologies shown here. This code essentially creates a new instance of the minimal topology defined above, creates a new Mininet network with that topology, a remote controller, OVS switch, and set automax to true. This is essentially the same as the Mininet command we ran in the console. Then drops the user to the Mininet command line. When the user exits the CLI, the network is shut down. If this Python script is run directly, it will set Mininet's log level to info, then run the minimal topology. To run this, make sure the Python script is executable. Then run sudo minimal.py. It then runs essentially the same as specifying the topology in the Mininet command line. This topology is very simple and could be written with just the minimal topo class definition and the topology registration code at the very end. As a quick aside, you may notice that while writing this code in Atom with the autocomplete Python package, available methods and variables will be shown while typing. Documentation for methods will be shown as well if available. Now that we've covered the minimal requirements for a Mininet topology, let's look at designing a topology that resembles a simple data center with top-of-rack switches and a root or aggregate switch. The data center basic code will create a single aggregate switch, set up 4 racks, each with a single top-of-rack switch connected to the aggregate switch, and 4 hosts for each rack connected to the associated top-of-rack switch. This is still a simple example and runs almost exactly like our minimal topology, except it breaks out the code to build the racks into a separate function so it can be reused. The build rack function defines a top-of-rack switch, then defines and links 4 hosts to that switch. The function returns with an array of the top-of-rack switches, in this case just a single switch. Later, more than one top-of-rack switch may be defined for a rack and will need to be passed to the calling code. Making this an array now and dealing with the return value as an array will make expanding the code easier later. The main build function for the topology creates the aggregator switch. A loop is iterated over an inclusive range of 1 to 4. That loop will call build rack with a number as the location. The array returned is then iterated in a loop to add a link between the aggregator switch and each top-of-rack switch in the rack, in this case just a single switch. In this case, switch 1 of rack 3. It is connected to hosts 1 through 4 of rack 3 and a link to switch 1, the aggregator switch. For naming, the switch and host names follow the Mininet convention of starting with S or H, then a number, followed by R and the rack number. At the end of the script, the topology is registered for running as a custom file in Mininet, and the short name for the topology is specified. In this case, DC Basic refers to the data center basic topology. Go ahead and restart Ryu. For Mininet, use the same command as before except for specifying the new file name under the custom option, and the new topology name under the topo option. Mininet has created all the hosts, all the switches, and all the links, then finally started the switches. It adds all the hosts and all the racks first, then it creates the aggregator switch, then the top-of-rack switch for each rack. During linking, the aggregator switch is first connected to each top-of-rack switch, then each top-of-rack switch is connected to each host in that rack. As before, it then configures all the hosts and starts all the switches. Performing a ping all shows that each host can connect to each other. This topology was successful and simple. However, we want to make this topology configurable, such as modifying the number of hosts or racks. Opening the data center configurable topology, it shows that it still has a single aggregator switch, but any number of racks and any number of hosts per rack. To do this, we add a couple parameters to the build function. One that specifies the number of racks and one for the number of hosts per rack. Mininet allows passing numbers to the topo option, and these two arguments will be supplied with these numbers. If no additional topology options are supplied to the topo option, the default supplied here will be used. This topology is very similar to the static topology prior, except that the number 4 is replaced with the argument supplied to the build method where required. This allows for a variable number of hosts and racks. The build rack method is modified to allow passing in the number of hosts that should be created in each rack. Finally, the custom topology registration is updated with the new names. Clean the environment as before. Change the topo and custom options to reflect the new names. Without specifying any additional parameters to the topo option, this results in the same exact environment as before by using the internal defaults of 4 and 4. Ping all results are the same. Let's say we want to change the topology. Here we can add a comma and the number of racks. Here it runs 2 racks instead of 4. It still works, but with fewer hosts as there are fewer racks. We can then add a comma and another number to specify the number of hosts in each rack, in this case 8. Now we have the same number of hosts, but the topology is changed so that there are 8 hosts in 2 racks with a total of 3 switches emulated. Again, ping all shows that all hosts can connect to each other. This can also be reversed so there are 8 racks each with 2 hosts, resulting in a total of 9 switches emulated, but the same number of hosts as before. A ping all confirms connectivity. This shows you can easily add some flexibility to your topology code without having to modify the code each time you want to modify the number of devices emulated or the shape of the network. Now that we have our basic data center configurable, let's look at making it a little more realistic. In a production environment, you may have multiple aggregator switches in a high availability configuration. A simple HA topology will have 2 or more aggregator switches linked in a loop. Let's look at the code for data center HA root. At the top, you can see that the aggregator switch section is modified so that multiple switches are put in a ring. Each rack will be connected to each aggregator switch so that any of the aggregator switches may fail without the rack losing connectivity if controlled properly. We could still specify a single aggregator switch and the topology will remain unchanged from the previous example. In this case, the topology will default to 2 aggregator switches and each top-of-rack switch will link to both of them. We still have the same parameters as before that allow specifying the number of hosts and racks in the topology. To add this ability, we add a new argument at the end that specifies the number of aggregator switches inside the existing build method definition. A check is also added to make sure we do not have more than 15 aggregator switches due to addressing constraints we made earlier. Now that we're dealing with more than one root switch, the definition for the single root switch is replaced with a loop much like the racks and hosts. References to those switches are kept for later use. In the loop, if there was a switch already defined, in other words this is the second or later switch, a link is added from that last switch to the current switch. The last switch reference is then updated to the switch we just created before the loop continues. This creates all of our right-hand links seen in the diagram at the top of the topology source, S1 to S2, S2 to S3, and so on. After the loop, if there is more than one aggregator switch created, it will create the final link from the last switch to the first switch, completing the loop. The rest of the code is essentially the same, except that instead of a single link created from a single aggregator switch to each top-of-rack switch, an additional loop ensures that each top-of-rack switch is connected to every aggregator switch. The build rack code is left unchanged. The name of the topology is updated as before. Let's run this, but first clean our environment by restarting Ryu and running Mininet with the new topology. After the Mininet network starts up, we immediately see non-stop traffic on the controller. This is caused by packet loops introduced by having multiple paths to each host. The Simple Switch controller application we've been running cannot handle this topology. Trying to ping all confirms that the hosts can no longer connect to each other, and the controller consumes 100% of the CPU available to the virtual machine. Trying to stop the controller forcibly by pressing Ctrl-C doesn't work at this point, because so many packets have been queued and the application is no longer responding. We have to shut down Mininet to remove the switches from the controller before it can respond. Once the packets stop flowing to the controller, it can now be stopped with Ctrl-C. Alright, we have loops. We need a different controller to run this network. Thankfully, there is a Simple Switch example with STP support provided by Ryu that we can use. Instead of Simple Switch 13, we will run Simple Switch STP. Now we will run the same topology as before. An initial ping all will show dropped packets because the topology is not completely learned by the controller yet. After a moment, the learning will finish. A second ping all will confirm that the hosts can ping each other with no dropped packets. Although STP serves well as an example for one way to prevent packet loops in a network, it is doubtful that it would be used exclusively in a high availability network. It does illustrate, however, that the controller needs to have knowledge of the topology of the network in order for that network to function properly. Now let's say we want to expand the multi-link redundancy to the hosts themselves. Full host to aggregate redundant links. That topology is in datacenter HAfull.py. This expands on the previous topology except there are multiple top-of-rack switches per rack. In this case, the number of high availability switches determines not only the number of aggregate switches, but also the number of top-of-rack switches. Each top-of-rack switch is connected to the associated aggregate switch. For example, switch 1 of any rack is connected to the first aggregator switch. The only changes we needed to make was to add the new argument to the build rack call that lets it know how many top-of-rack switches to create. And instead of having each aggregate switch connected to a single top-of-rack switch, the code is changed to connect each top-of-rack switch in the rack to its associated aggregate switch in the core. When building the rack, we now have a loop that covers the definition of each top-of-rack switch rather than a single switch. This is also where the 15 HA switch limit comes into play, as the DPID addressing can only support 15. This could be increased by changing the addressing scheme. However, it is very unlikely that a rack would have more than 15 top-of-rack switches. The naming is updated to include the new switch number for each top-of-rack switch. Then, for every host in the rack, we add a link from the host to each top-of-rack switch. Now let's stop the previous topology and start a new full HA topology. Again, during the learning stage, some pings will not go through. Eventually, the learning will complete and pings will start to go through. Running ping all again shows 0 packet loss. When designing topologies, it is often a good idea to write test cases, as you would with any other software. Provided with the article download is a test file that imports all the topologies and tests each one in turn. The test will also start its own instance of Ryu, so Ryu does not need to be running. To run the test, first close out of Mininet in Ryu. Then run the datacenter test.py file. Of course, like Mininet itself, it needs to run as root. This will take a few minutes as it needs to create a clean environment before each test. Start the topology under test, start Ryu with the appropriate controller, run the ping all test, then shut down the topology. When the tests get to the loop topologies, the ping all test will show a few packets dropped. The test cases account for a certain amount of packet loss to account for the learning process. All the test cases passed. This concludes the Custom Mininet Topologies overview video for the Inside OpenFlow article, Custom Mininet Topologies and Introducing Atom. We hope you've enjoyed this overview, and please check out the full article for complete instructions and explanations. Happy coding!